Hello, welcome back to EEE101. Today we will talk about mesh analysis. We already know that there are two generalized techniques for solution of electric circuits, and we have learned already about nodal analysis. Mesh analysis is the other generalized technique for circuit solution. In nodal analysis, we saw that the primary focus are on the voltages and the node equations are based on KCL. In mesh analysis, the primary focus is on current variables and the mesh equations are based on KVL. Before we proceed further, first let us understand what is a mesh. A mesh is the smallest loop which doesn't have another loop within. What does it mean? Let's look at the following circuit. In this circuit, we have actually three loops. Vs1, R1, R3 constitute one loop, R3, R2, Vs2 constitute one loop, and Vs1, R1, R2, Vs2 constitute another loop. This is the outer loop. The first two loops are meshes. Vs1, R1, R3. This loop does not have another loop within it. R3, R2, Vs2 also doesn't have another loop within it. So these are meshes. However, the outer loop Vs1, R1, R2, Vs2, this loop contains two smaller loops within. So this is not a mesh. We can summarize that this circuit has three loops but only two meshes. In mesh analysis, we will count the number of meshes a circuit has. In this circuit, we can see that there are three branches. Vs1, R1 constitute one branch, Vs2 and R2 constitute another branch, and R3 is the third branch. What does a branch mean? Branch means a part of the circuit which carries the same current. There are three branch currents in this circuit flowing through three branches. Let us say the three branch currents are IA, IB, and IC. Actually, these three currents are not independent. If we write KCL at this node, we can say IC is equal to IA plus IB. That means if we can find out two currents, we can calculate the third current, and from that we can determine any other circuit variables that we want to find. So we need to know two currents in this circuit, and 2 is also the number of meshes in this circuit. In mesh analysis, we assign a fictitious current which is called mesh current in each mesh. I1 is a mesh current which is flowing in the left mesh, and I2 is a mesh current which is flowing in the right mesh. What do we mean by fictitious current? A fictitious current is a current which cannot be measured with an ammeter in a real circuit. A real current can be measured with ammeter. The branch currents are real current, but the mesh currents are not actually real currents. Now we want to know what are the relationships between mesh currents and branch currents. To know that, we first decide what are the different types of branches we have in this circuit. There are two types of branch. In the first type, the branch belongs to only one mesh. If we look at Vs1 and R1 branch, this branch is only in mesh 1. It is not shared by any other mesh. Similarly, the branch consisting of R2 and Vs2 belongs to only mesh 2. This is not shared in any other mesh. If we look at R1, IA is the current through R1 from left to right. I1, the mesh current, is also the current through R1 from left to right. So I1 and IA are the same current. So I can write IA equal to I1. But if we look at mesh 2, IB is the current through R2 from right to left, whereas I2 is the current through the same resistance from left to right. So IB is minus I2. If we can combine these two relationships together, we can say that in this type of branch, which belongs to only one mesh, the branch current and the mesh current have the same magnitude. The other type of branch is common to two meshes. If we look at R3, R3 belongs to mesh 1 and it also belongs to mesh 2. So this is an example of a branch common to two meshes. We have already seen IC is equal to IA plus IB, which means IC is equal to I1 minus I2. That means the branch current is equal to the difference of the two adjacent mesh currents. This is important. We need to remember what are the different types of branches when we do mesh analysis of a circuit and what are the relationship between branch current and mesh current in each type. Okay, now in mesh analysis we want to write KVL and the voltages across the resistances will be expressed in terms of Ohm's law. Let's look at that issue in a little bit more details. We have a resistance R in which the current flowing from left to right is I. If V is equal to IR is the voltage across the resistance, from passive sign convention, we will put plus sign on the left and minus sign on the right. So when writing KVL, if we are going from left to right, V equal to IR will be a voltage drop. If we are going from right to left, the voltage V equal to IR will be a voltage rise. So we can generalize this by saying that in KVL, if we are going in the direction of the current through a resistance, the IR voltage is a voltage drop. If we are going in the direction opposite to the current, the IR voltage is a voltage rise. So this is how we consider the voltage drop across resistance using Ohm's law. So if we summarize again, if we go in the direction of the current, V equal to IR is a voltage drop, which is positive according to our convention. And if we go in the direction opposite to the current, V equal to IR is a voltage rise, which is negative in our convention. In mesh analysis, we will always write KVL by going in the direction of the current. So the voltage across resistance V equal to IR will always be drop, hence positive. We will not consider voltage rise or negative voltage across resistances in mesh equations. Okay, this is the principle that we will follow in writing mesh equation, which is based on KVL and Ohm's law. Now let's look at the two meshes of this circuit and write mesh equations. In mesh 1, we have three circuit elements, two resistances R1, R3 and the voltage source V1, Vs1. R1 belongs to only mesh 1, so the mesh current is I1, the branch current is also I1. R3 is common to mesh 1 and mesh 2. So when we look in the downward direction, the branch current through R3 is I1 minus I2. Please understand this. The branch current through R3 flowing in the downward direction is I1 minus I2. So if we write mesh equation for mesh 1, the voltage drop for R1 is I1 R1. The voltage drop for R3 is I1 minus I2 times R3 and Vs1 is a voltage rise. So on the left hand side, it appears with a negative sign. And algebraic sum of all the voltage drops is equal to 0. Similarly, if we look at mesh 2, we have two resistances R2, R3 and a voltage source Vs2. The current through R2 is I2. The current through R3 in the upward direction, when we are Mesh 2, we will move in the upward direction through R3. So in the upward direction, the current through R3 will be I2 minus I1. For mesh 1, the current through R3 was I1 minus I2 in the downward direction. For mesh 2, the current through R3 is in the opposite direction, so this is I2 minus I1. So if we write the KVL or the mesh equation, voltage drop across R2 is I2R2, voltage drop across R3 is I2 minus I1 times R3, and Vs2 is a voltage drop, so it is positive on the left hand side. In the next step, we can move the voltage source terms on the right hand side. So on the left hand side, we have the voltage drops across resistances. On the right hand side, we have voltage rises across voltage sources. From this, we can generalize the structure of the mesh equation, which can be expressed in this way. Sum of the voltage drops across resistors in a mesh is equal to sum of the voltage rises across voltage source in the mesh. On the left hand side, we have voltages of resistances, which are always voltage drops because we are going in the direction of the current. On the right hand side, we have the voltage source terms. On the right hand side, the voltage source terms are positive if they are voltage rise, they are negative if they are voltage drops. So this summarizes the techniques for mesh analysis. Now, if we want to identify the different steps, this can be written in this way. First, we identify the meshes in the circuit. Then we assign a mesh current in each mesh. It doesn't matter whether the current is clockwise or counterclockwise. However, all the mesh currents should be in the same direction, either all clockwise or all counterclockwise. Then we write the mesh equation in each mesh using KVL and Ohm's law by going in the direction of the mesh current. Finally, we solve the resulting equations to get the values of the mesh currents. Now let's look at an example. In this circuit, we want to calculate the mesh currents. By observation, it is straightforward to say that there are two meshes. We assign two mesh currents, both in the clockwise direction. In mesh 1, there are three resistors, 3 ohms, 45 ohms, 2 ohms. 3 ohms and 2 ohms belong to mesh 1 only, but 45 ohms is common to mesh 1 and mesh 2. For 3 ohms and 2 ohms, the current will be I1 because it is type 1 branch. For 45 ohms, we go downward, so the current is I1 minus I2. This is the second type of branch. And this 40 volts, if we go in the clockwise direction, is a voltage rise. So this is how the mesh equation will look like. 3I1 plus 2I1 plus 45, I1 minus I2 is equal to plus 40. Again, if we look at mesh 2, there are three resistances and one voltage source. 4 ohms and 1.5 ohms belong to only mesh 2. So these are type 1 branch. 45 ohms is common to mesh 1 and mesh 2. This is type 2 branch. When in mesh 2, we will be moving in the upward direction through 45 ohms. So now the branch current is I2 minus I1 in the direction of our travel. In mesh 1, the current was downward, I1 minus I2. In mesh 2, the current is upward, which is I2 minus I1. We need to understand this difference. Okay, so the mesh current for mesh 2 is 4I1 plus 1.5 I2, and for 45 ohms, it will be 45 I2 minus I1. On the right hand side, this 64 volts is positive because this is a voltage rise. Now we can collect I1 and I2 coefficients to simplify these equations, and we get these two equations. We have two equations and two unknowns. We can solve them in a straightforward way using our calculator, and the result is I1 is equal to 9.8 ampere and I2 equal to 10 ampere. So we can see that mesh analysis is quite straightforward, and if we understand the concepts of nodal equations, it is not difficult to understand the concepts of mesh equations also. In the example that we have studied, there was no current source. If we have current source in mesh analysis, that has to be handled as special cases, just like voltage sources in nodal analysis. We will see how to deal with circuits containing current source in mesh analysis in the next lecture. That is all for now. Thank you.